Hello friends, welcome to next video part 2 of Dibrugarh University paper solution of Web and Optics Physics Honors second sem, and this is 2022. This is the paper of 2022. So we have already solved question number 1, MCQ questions in the previous video. Link is given in the description box. If you haven't watched that, then please go through it. Link is given in the description box. Okay, so before we start, please subscribe the channel. If you want me to complete the whole paper, then please subscribe the channel, and in next 2 or 3 parts I'm going to complete this paper. Okay, and if you like my videos, then please hit the thumbs up button and share with your friends. Also hit the bell icon so that you get notified when new next part will be uploaded. Okay, so now this is the question 2a. Here, describe any one method for demonstrating the interference of sound. So to demonstrate interference of sound, we're gonna discuss we're gonna take the Queen's apparatus. Okay, this is the most popular method. So here you see it consists 2 tubes, U-shaped tubes. So this is A and this is B, and here you see this tube is fixed. This tube is fixed, and this can be adjustable. So now you see that means this tube B can be slided over this A, right? It can be pulled out, then pushed in, right, like that. So now you see, when a sound is produced by this source S here, and this sound will travel through this, and it will be divided and travel in 2 ways, right? And if we consider that the length of this fixed side is suppose L1 and this is suppose L2, right? L2 distance covered by the sound coming through this tube is L1, and this tube which can be adjusted, that is adjusted such a way that when these 2 sound waves travels this into these 2 direction, and they again comes to this point Q and interference each other, then combine, the resultant gives the maximum, central maximum. Suppose we have adjusted such a way, in that case the path difference that del L, which is equal to L2 minus L1, that's gonna be the integral multiple of lambda, so let it be n lambda, so it must be n lambda, where n is integer. So now you see, suppose this B tube is now pulled outside through a distance, suppose x, so then here you see the sound traveling through this adjustable tube will cover this x distance twice, right? So this B tube is pulled out through a distance, suppose x, right? Through a distance, suppose x, then the sound wave will cover this x distance twice, here and here, right? So hope you have understood this. So then the L dash will be here L2 plus twice x minus L1, and suppose now we have got the next constructive interference, that is suppose n plus 1 lambda, right? So now if you subtract these 2, 1 and 2, then what you will get? Then you're gonna get twice x after subtracting 1 from 2. If you subtract 1 from 2, then you will get twice x is equal to lambda. So lambda is the wavelength, so x will be equal to let us keep this way. So lambda is the wavelength of this sound wave that travels through these 2 tubes, right? And so hope you have understood these things, and I have taken this this from a book. Just I have clicked a photo and pasted it here. Here about this method is written here. Now let's move on to next question. So now here you see a note produces 4 beats per second with a tuning fork of frequency 5112, right? Hertz, 5112 hertz. 512 hertz, and 6 beats per second with another tuning fork of frequency 514 hertz. Find the frequency of the note. So let us consider the frequency of the note be suppose nu n. This is the frequency of the note, and as here this note produce 4 beats per second with one tuning fork of frequency 512 hertz. So therefore the possible frequency of this note, that nu n must be 512, either 512 plus 4 or minus 4. This is the possible frequency. So that's why we have got 512 plus 4 is equal to 516 hertz, and 500 and minus 4, that is 508 hertz. So similarly, this note produce 6 beats with 6 beats per second with the tuning fork of frequency nu 2, that is 514 hertz. And so that's why possible frequency of the note must be 514 plus 6 or minus 6, and 514 plus 6 is 520 hertz, and 514 minus 6 is 508 hertz. So here you see we have got this frequency in both cases, so that's why the frequency must be 508. The frequency of this note must be 508 hertz. So hope you have understood this. Now let's move on to next question. So here temporal coherence and spatial coherence, we need to write the differences. Here you see, so what is temporal coherence? Suppose this is a wave, single wave, and this is coherence up to a certain time interval, then phase changes, again it is coherence up to a in a another time interval, another time period, then we're going to say this is temporal coherence. Okay, it depends on time, right? So if you observe different phases at different times, right? So now suppose we have two waves. Suppose this is one wave and this is another wave. So let me draw this way. This is one wave and this is another wave. Suppose, let me use two different colors, right? So now let us consider these two particles, here. Then so let me consider another two particles. Suppose just wait. So let me take a new slide here. You can write the answer from here or this table directly. So let me explain the spatial coherence in the next slide. So here you see, suppose you have two waves. Let me draw the waves first. So here you see, suppose we have taken 2 points here. Let me use the rating here. This is 1 point and this is another point here on the two waves. So here you see clearly that the phase difference between these 2 points is pi by 2. They have a phase difference of pi by 2, right? So they have a phase difference of these two particles. This is suppose P1 and this is suppose P2, having phase difference pi by 2, right? So when they will travel, that means when P reaches to this point, here the P2 comes here, sorry, not P2, P1, and this P2 will go there, right? So now at this time also they have phase difference, right? So as these two propagate, now if the phase difference between these two remains constant, right? Then this will be called spatial coherence, right? So hope you have understood this. So here is the next question. Explain the term fringes of equal inclination. Now you see these fringes are formed by parallel incident beams from an extended source. These fringes of equal inclination are focused by a lens. So here you can see the diagram. So this is this extended source, and from an extended source these parallel lights are coming, and they are reflected from this top surface as well as bottom surface. This is a film having a thickness suppose t, let me consider that way. So then they will be reflected, they will be reflected from the top and the bottom surface both, and then after reflection they remains parallel, okay, and there must be a lens here, right? This is a lens, and here we get fringes of equal inclination. Okay, so we can write that fringes of equal inclination, fringes of equal inclination fringes of equal inclination result when light from an extended source falls on a thin film made of optically denser medium, made of optically denser medium. Made of optically denser medium, and these fringes incident sorry, not incident, wait, indicates the position where light interferes emerging from the medium at an equal angle, right? So this is all about fringes of equal inclination. So now you see, let me go to the next question, that is 2e. The last question we're going to discuss in this video is question number 2e. Okay, next questions will be discussed in the next video. Remaining questions will be discussed in the next video. So here we need to describe the Kirchhoff's integral formula. Here we are not going to derive that, just we need explanation on this integral formula. So here all about the Kirchhoff integral formula I have it is written. I have taken those from Google. So here this also known as Fresnel's Kirchhoff integral. So this is used to derive the solution of homogeneous scalar wave equation at arbitrary spatial position p in terms of the solution of wave equation and its first order derivative at all points on arbitrary closed surface S as the boundary of some volume including p, and the solution provide the integral theorem for monochromatic source is this. So here you see
And what are the terms, meaning of the terms that we have used here, those are already mentioned here. And if we go to next slide, so what are the consideration made here, this is written. And what does it represent, these are all already mentioned here. Motive of this video is not to explain the concepts here. My aim is to provide you the answers only, so that's why I'm not explaining this in details. So here you see, and the disturbance at spatial point P can be found by applying Kirchhoff's integral theorem to closed surface formed by the interaction of a sphere of radius r, capital R, with the screen, and the integration is formed over the area A1, A2, A3. So here this is A1, sorry, not A1, this is A2, right? So here is the A1 and this is A3, and combining A1, A2 and A3, so this whole surface is composed of these three, right? So here you see these are the assumptions made, and this is the Kirchhoff's integral formula, which gives the disturbance at the point P, right? So see you in the next video. If you like my videos, please share with your friends, hit the thumbs up button, and help me to grow my channel. And if you are new to my channel, please subscribe the channel. Stay connected.